Hello guys, I'm Abel Verma and welcome to the part 2 of creating an 8-bit computer using 6502 microprocessor. So in part 1 we discussed basically how an ALU works and how a CPU takes an input, how it gets an output, and pretty much that's it. That's very basic of a computer when we talk about doing any kind of calculation. Today we are going to see how basically we connect an ALU with other components such as RAM or ROM, and that will actually clears a little bit of a picture how a motherboard basically made of. So in our previous video I told you a very simple thing, which is a CPU basically takes two inputs A and B, give one output C, and all these are 8 bits when we talk about an 8-bit computer, and there will be a clock signal which basically tells how a fast processor is going to work. This clock signal connects to some kind of a timer circuit, and in most of the cases it's some kind of crystal, and in case of microprocessors it's mostly like 555 timer circuit, which we will make when we are going to create our computer onto the breadboard. So we'll try to create a 555 timer circuit to basically power our CPU. That was all we discussed. Now we're going to discuss how basically a microprocessor connects to its ROM and RAM, and how basically address bus or data bus works. Okay, so I think this much is pretty much clear. So now let's talk about one problem that we may have when we talk about a processor. So let's say we want something like A plus B, which is going to give us C, and then we're gonna do something like C plus something, say D, and we need to get an output E. Let's say we have to do some kind of a binary operation or some kind of an addition in binary in this kind of a manner, and we of course know that a CPU is going to take two inputs A and B, which gives an output C. Now a problem arises when we need to, of course there's a clock signal, but I'm not going to show it, we know that it's working. Okay, so now the question arises how basically we can store this value of C, so that when the next clock input is going to when the next clock is going to hit, we can perform this C plus D. There comes the logic, what we call a register. So a register looks something like I think a NAND gate or a NOR gate. So I'm using a NAND gate. So a NAND gate looks something like this, I hope so. And so what a NAND gate can do, so when we create a circuit something similar to this, we take two NAND gates, and from the output of one NAND gate, when we connect to the input of other NAND gate, and the output of the second NAND gate we connect to the input of the first NAND gate, then we extend these and we extend these. We can call it as A, we can call it as we can call this thing as C, and this thing as reset, and we call this thing as C bar, or inverted of C basically. Now this concept is given by, I actually learned this concept by the same person which I recommended in my last video, the Mad Max, which actually explains how a latches circuit works, and this particular diagram is known as a latcher circuit. And a latcher circuit basically do one thing: it is going to store a value. So when we give, let's say, 1 over here, for the first time, what is going to happen, the C becomes 1 and it remains 1. Now if we just change value of A to 0 or 1, it won't change until unless we try to set 1 on this R, or the reset button. And I'll tell you in a minute why we call this as a reset. As we give 1 over here, this C become, and basically when we give 1 over A, the C bar or the C inverted becomes 0. And when we give 1 on reset button or the reset pin, C becomes 0 and C bar becomes 1. That's it. That's all it does. So when we give 1 and we didn't change the value of reset, any value we change, either we make it 0 or 1 in between, the value of C remains 1 itself. How we can use this circuit to solve the problem which we discussed in the previous slide. Basically what we require is to save the value of C, and in this circuit, if you see, when we change the value of A to 1, then the value of C becomes 1. That's all and then afterwards, if we change it to 0 or 1 or anything, it doesn't matter to C. It remains 1 until unless we change reset pin or R to 1. If we change it to 1, this becomes 0. Now let's say we compile this and put this thing into 1 unit. So let's say we have 8 of those units like this. Okay, that's 1 2 3 4 5. Okay, there's one more box. So every unit is going to have 2 pins coming out, and 2 pins from the other side. Now first pin, I'm gonna call it as A, so I'm not gonna write on every of them, so I'm just typing here A, and the second pin, which is going to be R over here. Now what we are going to do is basically we are going to extend these A's, this 8 wire of A, something similar to this, and we're gonna connect all the reset wires to each to a one single wire, something similar to this. So this all 8 inputs becomes the A's, and all the reset wire connects to one single wire and become a reset pin. Now this side is C and this side is C bar or C inverted. Now we extend C to this length, so we have 8 pins coming out of C. Now let's compile this one big unit into one IC, something similar to this. So we have 8 wires coming out, 1 2 3 4 5 6 7 and 8, called as A. One wire coming out as a reset pin, and 8 wire coming out as C. We don't consider C inverted. Basically we don't take the C inverted as an pins in a register. This is known as a register. Okay, just write reg here because reg is a short form of register. This is how we can store a value. So whenever we are going to provide any 8-bit number which is A, and this value will be stored on to C, and until unless we don't change anything, if we just keep on changing values of A, the first value that we give to this circuit will be saved here. Other values will remains unaffected, is not going to affect the value of C until unless we connect this thing to 1, or we give 1 on the reset, or basically we just power this pin with 5 volts. And as soon as we power this thing with 5 volts, the value of C becomes all zeros, and it means it basically clears the value of C, and then we can set the another value of A. But there's one small thing in this particular case, and that is set pin. Now how set pin works? Basically set pin is very simple. When we consider these 8 wires, okay, I'm just gonna zoom in, something like these are the 8 wires of input A, and we connect them to an AND gate, something like this. And then we connect these wires to the IC which we discussed in the last slide, which is our resistor. And the other pin of AND gate, we can connect it similar to the reset pin to one single wire. Okay, I'm not very good in drawing this, but still you guys can understand that. We can call this as set pin, and this becomes our A. What this is going to do, and this is basically going to get into our resistor which we discussed in the last slide. This becomes the input of our resistor. So what we understand from this, now if we take this value as 0, any value that we set in our A, or the input A, it won't affect these things. This will still remains 0, because when 0 and 0 is becomes 0, 1 and 0 is 0. So any value, whether it's 1 or 0 on any of these bits, won't going to affect these values. But when we change this to 1, what happens? 1 and 1 is 1, 0 and 1 is 0. So it means when we set this set value to 1, any value that we set on this particular bit will going to be stored in our C, which is the output of this register. So the complete picture looks something like this. We have an input A, we have a set pin, we have a reset pin, and we have an output C. Again, A and C are 8-bit numbers, set and reset are one single values. Don't get confused in that. So when we want to set any value to C, we set this set pin to 1 and give the value on A, then C is equal to A at that time. Then we change set value to 0 and it fix it here. It won't change. Then it will change when we set reset value to 1. That is going to reset the register, and then C becomes 0. And we remove, then again change reset value to 0, and then we can set again, for setting the new value we can set value to 1, set the new value, C becomes A, and then we reset it. So it's basically like we can set any value and we can reset it back to 0. Now is one thing that we achieved through this circuit, and that's these components. This is ROM and RAM. We achieved RAM with the help of this circuit, because if you look into the surface, in the circuit, basically that's what RAM do. It stores a value temporarily. So when we have a lot of these circuits arranged in a form of a matrix, and each cell of a matrix can store 8-bit of value, something like this, then it basically becomes a RAM. This all connects here this way. These are the 8 bits, plus all connects this way, which is also an 8-bit. So we have 8 set of wire this, 8 set of wire this, 8 set of wire this, similarly this. These are all 8-bit numbers. So when we set this one, all 8 set some value to this pin or this input, and similar to same value we set it over here, then that corresponding cell actually stores that value, and that's what RAM does. So this cell and this cell will going to affect this particular unit. Similarly, this cell will going to affect this particular unit, and we can store our 8-bit number into our RAM in this way. But who is going to decide which cell to select, which particular row to select, and which particular column to select? That is known as address. It's similar to our Excel sheet, where if you have worked on Excel, we know we name Excel rows with numbers and columns with A, B, C, D. So if we want to denote any particular cell, it becomes A1, A2, A3. In the same way, RAM also works. So RAM has these rows and columns, and the particular row which is going to affect particular cell, and we need to reach up to that point, then we tell RAM to basically, in the form of 8-bit number itself, to address that particular cell. So the addressing of a RAM is also an 8-bit number. Using that 8-bit number, a RAM is going to decide which particular cell to address. That's it. And the same way with ROM. The only difference is ROM is not going to lose its whatever values it saved, even after you remove it from the circuit completely. If you just don't power it, it will remain non-volatile. RAM is a volatile. Plus we talk about one more thing, that is register. And so we come back to that particular problem where we have a CPU with 2 inputs A and B, and one output C, and a clock pin. Basically we want to add A plus B, which we get C, and we can, using our register, basically we can save C, and this will become C by setting the set pin to 1. Now what we are going to do is, basically we are going to set C instead of A and our D value instead of B. And how we are going to do this? We can connect this pin right up to this point, and we can set a new value to D, and then we can give another clock pulse, which is going to give our output as E. But this looks complicated. This is not the way CPU is designed. We need some kind of a, what we can say, some kind of an arrangement which basically can help us to manage our flow of inputs and outputs. That's why, to manage this clumsy way of transferring values from one processor to register, from register to RAM, ROM, or anything, the computer guys, they actually came up a very good solution, which is known as the bus. So this is how a CPU looks like when you consider everything. There's going to be a bus. This is a bus. A line. No, it's not a line, it's a 8-bit number. So of course, if it's 32-bit number, it's 8-bit number, so it means it's going to be a set of 8 wires going in a straight line. Okay. If it's 32-bit computer, it's going to be a set of 32 lines, 64 lines. Now we create something similar to this. and we have C coming out, which is again going back to the same bus. We have a RAM which has again an input of an 8-bit number. We call it, let's say, I. We have few registers which can store only one 8-bit number. RAM can actually have two things. One is a data which is coming inside, one we need is an address, and we're gonna talk about the address in just a minute, okay, because this is just a data bus. So this is going to be a register, and there can be a ROM as well somewhere in the same bus. In the same bus we can have few other things as well, something like a video chip, and we can have a sound chip. Whatever we want to connect to our computer, it is connected to the data bus. There's one more bus which is known as the address bus, which is right here. I'm showing right now this pin as floating or something, but it's not floating. It's connected to the another bus which will be parallel to the data bus, and the address part of the RAM, ROM or video chip or sound chip, whatever chips we have, will be connected to the address bus, but we will going to come at that point just in a minute. So every RAM, ROM and sound chip and everything is connected to an address bus as well. Address bus is going to define which chip needs to be activated, and whatever I'm telling you is now going to be a part of our 6502 computer that we are going to build. So let's say we want to set a value of A. So there is going to be a keyboard connected to our bus. I'm just representing with two numbers. So this is a keyboard, and this keyboard we are going to give a number input as 10. That's 10 is in binary, not in binary, it's in decimal. 10 will be converted into an 8-bit number by the IC which is installed on a keyboard, and this IC is going to put that value 10 in our bus. So every component over here can access that particular value from the data bus. Then a processor is going to get a clock signal from the clock. Then our processor is going to decide whether this value of 10 should be saved in A or should be saved in B. How it's going to do that? Again, it is going to, there's an AND circuit attached to each and every input of A and B, and the output of A and B is again going to the processor's address unit or the address line, not to the clock signal. I'm sorry about that. It is going to the address line, which basically defines which okay, let me draw this address bus as well so that it doesn't bother us anymore. So this is an address bus, and the processor or the CPU is going to set some value on the address bus, which basically decide which particular component to address. We are going to discuss how address decoding works, but this address bus is again going to be an 8-bit number which is set by our CPU itself. It is going to set there some value on our address bus, which is going to connects to these OR gates of each and every component, and these OR gates becomes true when that particular address line becomes 1, which is connected to that particular OR gate. Let's say the CPU wants to set the value of A. Let me just zoom in because it's very clumsy here so that you guys can understand. Okay, that's good enough. So these are the OR gates which you see, and let's say CPU wants to set the value of A. So it will change its address bus to somehow that the wire or the signal which is connected to the AND gate of A becomes true. So when the AND gate of A becomes true, the A will going to get the value from our data bus. Now there's another register attached at the point of A. So the AND gate is going to activate that register, and the register which is attached to input A will save the value. Then we give another input which becomes B, and the same happens with the B. Now we have two registers which has the value of A and B, and their output is basically going to our CPU, something similar to this. So this is a CPU, this is going to be a register, this is going to be our A signal, and this is going to be our set wire of the input A register, and similar to, there will be another register having a set wire for our input B, which is again going to the CPU. These set wires are connected to our, I'm sorry about that. So this is the complete structure. I didn't saw the camera, I was busy in drawing. So this is the complete structure, and again there will be an output C connected to a register which we get from here, and it is also going to have a set value. These set values are connected to the address bus, which we showed in our last diagram. Now, as the CPU is going to give some value to our address bus, these registers are going to be, receive some value on their set pins. Let's say A receive, for the first time A receive as 1, and all these are 0. So the data which is coming on the database will going to set our A register. Similarly, when the next clock hits, the CPU is going to set our address line in such a way that A becomes 0 and B becomes 1, and the next value which is coming in our data bus is going to tell our B input to save the next value which is on our data bus. And in the next clock pulse, the CPU is going to do some processing and going to save the value of the A plus B onto our C register by setting this value to 1. That's why we need a clock pulse, that's why we need a register to do all this sort of processing. And then the value of C is going to be saved in our RAM, which is going to be further used when the next D value we are going to insert through our keyboard. And pretty much that's it. That's what CPU does. We keep on giving input, it keeps on processing it and getting the results and output it on our data bus. So now we understood, like, there is going to be a data bus, and there is going to be an address bus. Data bus basically going to decide what data needs to be processed onto our CPU or onto our computer. Address bus is going to define which particular components this particular data is going to be used by. If it's ROM, then there is a specific address for a ROM. If it's a RAM, then there is a specific address for a RAM. And if there is a keyboard or if there's a monitor, everything connects to our address bus and the data bus. So let's say we want to display some character on our monitor, then it's going to have some address values assigned to that particular monitor. And whenever our CPU is going to set that particular address onto our address bus with some particular data on our data bus, our monitor activates and receive that data and going to display it on the monitor. Okay, I'm sorry about that. So I think that's pretty much it for this video. So we are going to continue in our next video where I'm going to start wiring our 6502 computer. So pretty much that's it. Thank you very much.